Hello everyone, my name is Liyan Wang. I'm going to present on vector-to-sequence models for sentence analogies, which is a joint work with Professor Lepage at Waseda University. I will start with a brief introduction about analogy and its applications to natural language processing. I will also describe some existing methods for solving sentence analogies. And then I will focus on our methodology and show the main results for the experiments. Analogy is felt as a way of imitating human cognitions. It's defined as a reasoning tool in symbolic artificial intelligence because it has the capability of capturing relations. Typically, it's noted as A is to B as C is to D. Each of four terms may be words, sentences, or other textual units. Here we have some examples. The first one, cat is to cats as dog is to dogs. This analogy encapsulates one category of syntactic relations. That's the regular nouns plural. The second one holds the word knowledge. It reflects the relations of capital and country. And the last one is an example for analogy at the sentence level. Because analogy can be used to explore the linguistic features, it has been applied to complete some NLP tasks, like machine translation and question answering. In one case of machine translation by analogy, for translating a sentence, we could first retrieve similar sentences in source language from bilingual corpus to construct the upper analogical equation. It's easy to find the translation of retrieved sentences. We could generate the translation for the input by solving the analogy in target language. In the task of question answering, analogies mostly are made of two QA pairs. It has been confirmed that analogy is good for learning features from the limited size of data. We focus on solving sentence analogies. Given a triple of sentences of an equation, the goal is to infer the answer sentence D that satisfy the analogical relations as much as possible. Some of previous work tackled this problem formally by analyzing the differences between four entities, decomposing the analogies into size of sub-analogies between words or characters. And they finally commutate or combine the pieces together as the solution. Some people have proposed the neural editor to encode transformation between two sentences. They applied edit vector that representing the relations in the sentence pair A and B on the sentence C to generate the answer. The correct answer may appear in their top 10 predictions, but this model cannot directly generate the correct answer. Due to the success of vector offset methods for solving word analogies, some people extend this method on sentence embeddings. They use linear operations to compute the vector for sentence D and identify its nearest neighbor from a set of candidates. However, the lack of decoders for sentence vectors limited the research to identifying the answer from the known candidates. It's also questionable whether simple linear operations are suited for solving analogies between sentences. To remove these limitations, our contributions are we first train decoder models to transfer sentence vectors back into a sequence of words. Based on this decoder, we introduce a network-based solution for sentence analogy. It frees us from choosing amongst a set of candidates. It also able to generate more reasonable representation for sentence D and performs better than the widely used approaches like the vector offset method. In this section, I would first describe the decoder model for sentence vector. We want to generate sentences on the premise of having only a fixed size vector and no other information. Our approach is inspired by training a sequence-to-sequence model for monolingual translation, and the input and the output are the same sentences. We use pre-trained sentence embedding model to encode sentences and take the sentence vector as the context vector. So we just focus on training the decoder model. The architecture of our decoder model is similar to the decoder part of our encoder decoder. We concatenate the input tokens embedding and sentence vector with the output of unidirectional RN layer to predict the next token at each time step. For the purpose of remembering the order and the representation for words, we propose the multi-loss function for training the model. Like the most work on training sequence-to-sequence model, we use a cross-entropy loss function to perform multi-label classification. Besides that, we add the regression loss function. We expect the output is very close to the embeddings of the next input words. Before we decode sentences from embeddings, we trained a network to predict the representation of answer sentence given an analogical equation. We establish a linear regression network to learn the mapping between given sentences and the correct answer in the embedding space. And we experiment with 3 compositional methods on the vectors of known sentences. Since we want the generated vectors to be as close as possible to the correct solution of sentence analogy in the embedding space, we use the MSE as our objective function. Here is a running example for solving a sentence analogy. We first use a pre-trained sentence embedding model to encode known sentences. After that, we apply a compositional method on 3 vectors to obtain a single vector that embed the features of this analogical equation. And then we use regression network to predict the representation of the answer sentence. Finally, we use pre-trained decoder to decoding this vector into sequences. In terms of data we used in our experiments, we first trained the decoder on English sentences from Tatoeba corpus. Then we evaluate our proposal on a semantical formal analogy set. We compare the performance of various decoding methods with different architecture trained on 2 typical sentence embedding models. There are about 63% of tests that are perfectly answered by the decoder. ML can learn for summation over fastest vectors. The predict sentences are exactly match their reference. But the metric accuracy cannot judge other kinds of valid results, which differ in form but not in meaning with the reference. Then we look at the results of antecedents. The generated sentences differ from the reference sentences by 1 word in average. So we can conclude that our model is able to restore the correct order of the words and a semantically similar text as the input. Our models perform significantly better than retrieval in the nearest neighbor sentences. As for 2 embedding methods, the summation over word vectors achieves better results, although the sentence representation based on word vectors fail to encode the order of words. This is the opposite of what we expected. So we look into the nearest neighbors against two embedding methods. We found there are some cases that both scores are inconsistent with human judgment. For solving sentence analogies, we select the best decoder as a part of resolution. Our approach performs better than the state-of-the-art method, especially the vectors composed by arithmetic analogy encapsulate more effective information for representing the non-synthesis of analogy. And our model can predict more reasonable representation for the answer. The worst result of the vector offset method indicate that the linear operation is not a good way for predicting the answer sentence representation. This table shows some results in the resolution of sentence analogies. Our model performed perfectly for solving analogies where the added distance between any two of the non-sentences is less than half of their length, such as the first example. The prediction is exactly matched the reference sentence. And some of our results, like the second and the third example, are semantically similar to their reference and even more reasonable. So to some extent, our model can enrich the diversity of the analogical set. And also, if the tokens of reference is unknown for the decoder, this kind of analogies are difficult to solve by our model. To conclusion, we introduced decoder model for decoding sentence vectors, especially decoders trained for multi-loss objectives performs better for returning semantically similar text as the original sentence. We also propose a regression network to learn the matching between the known sentences and the expected answer. Based on those, our model frees us from choosing results among a set of candidates given in advance, so we can directly generate the resolution. And the simple linear operations are not suited for solving analogies in sentence embedding space, but our regression network performed well. The matrices we used measure well the formal features, but they not well in the semantic level. So in the future, we will add the use of matrices like birth score to measure semantical features between sentences. As for the decoder model, the introduction of conditional reward may lead to better generation of semantically meaningful words, so as to solve analogies that include the unknown words. This work was supported by a grant from the Japanese Society for the Promotion of Science. Thank you for listening.